Today we're going to be talking about how to use implicit differentiation to find partial derivatives of multivariable functions. And in this particular video, we're going to be doing two different problems. One, y cosine of x equals x squared plus y squared. Notice in this equation here, we only have two variables, x and y. And then another, e to the z is equal to x, y, z. And notice that in this equation, we have three variables. The process for finding partial derivatives of these two equations will be slightly different because we have two variables in one and three variables in the other. So let's start with the simpler case where we just have two variables in this function. The first thing we want to do is move all of the terms to one side of the function, thereby setting it equal to 0. So in this equation, what we'll do is subtract y cosine x from both sides to get 0 on the left-hand side. So we'll get 0 equals x squared plus y squared minus y cosine of x. And now that we have 0 on the left-hand side, we can basically call this function capital F of xy is equal to x squared plus y squared minus y cosine x. Now the reason that we wanted to do that is so that we could get a function for capital F of xy, because in our formula here, the formula we're going to be using, notice that we take the partial derivative of this function here for capital F. So in order to get a derivative for y in terms of x, which is what we'll want, since when we have an equation in terms of x and y here, we want a derivative for y in terms of x. When we get over here, since we have an equation in terms of x, y, and z, we'll want a derivative for z in terms of x and y. We'll get to that in a second. But here we're going to want dy over dx. So to get dy over dx, notice that we're going to need the partial derivatives of this f function here in terms of x and in terms of y. So let's go ahead and find these two separately. We'll say the partial derivative of f with respect to x is going to be equal to, and now over here on the right hand side, we'll take the derivative with respect to x, treating y as a constant. So the derivative of x squared will be 2x. The derivative of y squared will be 0 because y is a constant, so y squared is a constant and the derivative of any constant is 0, so that'll go away. And then here for minus y cosine of x, the derivative of cosine here is negative sine. Remember that y just acts as a constant coefficient on this cosine of x. So since the derivative of cosine is negative sine, that negative on the sine will cancel with this negative and we'll get plus y sine of x, and that'll be our partial derivative of f with respect to x. Now if we get the partial derivative of f with respect to y, we'll treat y as the variable and x as the constant, so the derivative of x squared will be 0, the derivative of y squared will be 2y, and now here the roles are reversed. Negative y here is the variable part of this term. Cosine of x, since x is a constant, this cosine of x acts as a constant coefficient on the y variable here. So we'll really just end up with minus cosine of x, because this whole term here, when we treat y as the variable and x as a constant, that's really no different than, for example, negative 3x, where this negative 3 is the same as negative cosine of x, because this whole thing here is just a constant coefficient, which is right in front of this y. That's going to disappear. We're just left with the negative 3. And here we're just left with the negative cosine of x. So those are our partial derivatives. Now we need to plug them into our formula here. So our formula for dy over dx, the derivative of y with respect to x, don't forget this negative sign here. That's part of our formula, and it's super important. We have to include this negative sign. So we have negative, and then the partial derivative of f with respect to x. We already know that is 2x plus y times sine of x. And then in our denominator, the partial derivative of f with respect to y, we already know that is 2y minus cosine of x. And there we have it. That is our partial derivative of y with respect to x. That's how we find it. Now, if we look at a 3-variable function where we have x, y, and z here, we're looking for the derivative of z with respect to both x and y. Well, because we have z with respect to x and y, 2 variables with respect to 2 variables, instead of, in this case, with respect to just 1 variable, x, we're going to need partial derivatives. So our final answer will actually be the partial derivative of z with respect to x and the partial derivative of z with respect to y. We'll have 2 separate equations, one for each of these partial derivatives, and that will be our final answer because we have 3 variables here. So we're going to need to find these separately. The way that we're going to find the partial derivative of z with respect to x is similar to the way that we tackled this first problem. First, we're going to subtract e to the z from both sides to get a equation for capital F of x, y, z. We'll have 0 here on the left-hand side. We'll replace that with capital F of x, y, z, and we'll get x, y, z minus e to the z, like this. Now what we know is that the partial derivative of z with respect to x is negative partial derivative of f with respect to x over the partial derivative of f with respect to z. Similarly, the partial derivative of z with respect to y is negative partial derivative of f with respect to y all over partial derivative of f with respect to z. So those are going to be our formulas. We need to find these 3 partial derivatives. So we'll say the partial derivative of f with respect to x will be, remember, treating x as the variable, y and z as constants. The derivative of x, y, z will just be y, z. The derivative of e to the z will be 0 because there's no x variable involved there. The partial derivative of f with respect to y will give us x, z for that first term, and then 0 for the second term because there's no y variable involved in this e to the z term. The partial derivative of f with respect to z will give us x, y for the first term, and then minus e to the z because the derivative of e to the z is just itself e to the z. Now we can plug each of these 3 into our formulas down here. So notice in the numerator here we have partial derivative of f with respect to x, which we know is y, z, divided by partial derivative of f with respect to z, which we know is x, y minus e to the z. Then for the partial derivative of z with respect to y, and of course we can't forget our negative sign out in front here. That's super important. Just like before, we have this negative sign here. Then for the partial derivative of z with respect to y, we'll have again the negative sign here. Partial derivative of f with respect to y, we know here is xz, so xz, divided by partial derivative of f with respect to z, which we know again is xy minus e to the z. And that's it. These 2 equations together, right here and here, are our final answer for this partial derivative problem with 3 variables, where this equation here is our final answer for the partial derivative of this 2-variable equation here.